Okay, 8.6, the intersection of planes. So we've done intersections of lines with a plane. So now we're going to do with intersections of two planes as well as three planes. So let's start with the two-plane case. So given two planes in 3D space, we have several possibilities. One, we have two planes here where they intersect. The intersection is a line, okay? So the way we're going to determine that this is one of the conclusions when we have two planes is by looking at the normal. So if I look at the normal of this plane here, and I just want to draw a little perpendicular vector to that plane, and if I draw, let's say, a vector here that's perpendicular to that blue plane, we can see here the vectors, these normal vectors are not parallel. So we're just going to make a note of that. The normals are not parallel, okay? So in terms of writing this as some notation here, we can say the normal vector, one of the normal vectors is not equal to the other normal vector or a scalar multiple of the other normal vector. Okay, so as an example, you could have a normal vector that is given as, let's say, some arbitrary numbers, 1, 2, and 3. And if the other vector is not a scalar multiple, such as this, 0, 8, and -1, well, then we can say that the planes are distinct planes that intersect, that have a line of intersection as their intersection. Okay. The second scenario is if you have two planes here that are coincident. So if we have a plane here, there's a normal vector here, and then the blue plane below it, sort of also has a normal vector. We can see here that these two normal vectors are going to be parallel to each other, right? So the normal vector n1 is going to be equal to some scalar multiple of n2. Okay. Now, well, first of all, that proves that the planes are parallel, but what proves that they're coincident? Well, we have to also check if a point on one plane exists as a point on the other plane. So that would mean the equation of one plane would end up being a scalar multiple of the equation of the other plane, or they could be the exact same equation, right? So for example, if I had x plus y plus z as the scalar, or a -3 equals 0 as a scalar equation of one of the planes, and let's say I had 2x plus 2y plus 2z minus 6 equals 0 as a scalar equation of the second plane, well, you can clearly see that one equation, the first equation and the second equation are related, that because the second equation is just, equation 1 multiplied by 2, right? So that is what we mean by having the planes sort of, represent the same plane, the equations representing the same plane. So in essence, even if you don't have, even if you're not talking about the equations themselves, all we really need to do is say if we can find a single point on one of the planes, x, y, z, and that point, we can plug that point into both of these equations, and we find that they work, they exist on both the first plane, and we also check if that is also on the second plane, then we know that that both planes are coincident. They are the same plane, coincidence. So they are the same plane, right? Okay. And then the third scenario is we have two planes, okay, and they both have normal vectors pointing up. These two planes are parallel, but they have, in this case, there's no solution, right? If they're coincident, then every point is a solution. That every point that's on those planes are a solution. But if they are just parallel but still distinct, then there is no solution. So the difference between this third case and the second case is that, well, the n1 is still a scalar multiple of n2. The normals are still parallel to each other, but the planes, the equations that represent the planes, are not scalar multiples of each other. So a coordinate point on one plane will not work in the equation of another plane. Okay, so an example is, yeah, if I had x plus y plus z minus 3 equals 0 as the first plane, and then the second plane, well, it could be 2x plus 2y plus 2z. Oh, it looks very similar. It looks like a scalar multiple each other until I do something like this. minus 5 equal to 0, and now they are not scalar multiples of each other, which means they are distinct planes. And so if they're distinct planes, they can still be parallel, but they will not intersect. Okay, so those are the three scenarios. I'm sort of giving you this idea of how do we determine which one is which when we are given an equation of two planes. So like here's an example. If possible, determine the line through which the planes in each pair intersect. Okay, so we can see here that hey, 3 to 6 is a ratio of 2, 2 to 4 is a ratio of 2, but 1 to 3, that's not a ratio of 2. So right away we can see the normals to these planes are not parallel. Okay, and so what does that mean? It means, well, when we solve for this equation, when we solve these two planes to find an intersect, we're going to see that they intersect in a line. So let's just write that formally here. N1 equals 3, negative 2, and 1, and N2 equals 6, negative 4, and 3. And we're going to say here that N1 is not a scalar multiple of N2. And so if that's the case, then they're not parallel. They will intersect at a line. Okay, just like this first diagram here. Normals that are not parallel, they will intersect at a line. Okay, so how do we carry out this solution? So step one, eliminate one of the variables. So you're going to use elimination here. This is a set of equations, right? Two equations with three unknowns. So I'm going to show you how this works when you have three unknowns, x, y, and z. I'm going to start by writing the first equation, 3x minus 2y plus z equals 4. Okay, and yeah, so the plus d on the left side is now on the right side as 4. Okay, so that's okay too. I'm going to write the second equation, 6x minus 4y plus 3z equals 7. Okay, so let's call that equation 1, and here is equation 2. Now, if I took equation 1 and I multiplied it by 3, right? So here in this example, I'm choosing to eliminate z. So let's do that. So I need to multiply it by 3, right? I need a 3 here in front of the z so I can cancel it out. So if I multiply equation 1 by 3, I'm just going to write it here below. 3 times 3 is 9x. 2 times 3 is 6y, and then plus 3z equals 4 times 3 is 12. Don't forget to multiply the right side as well. Okay, so I'm just going to take these two equations, the second line, now my third line here. I'm just gonna subtract them. Okay, it takes, eliminate the z. So 3z minus 3z is 0. 6x minus 9x is minus 3x, and then minus 4 take away negative 6, so it becomes plus 6. So it's plus 2y, and that's equal to 7 minus 12, which is negative 5. Okay, so yeah, so remember there's a 0 z. We eliminated z. That's the goal here, right? So if I simplify this now, I'm going to have minus 3x plus 2y equals negative 5. Okay, so normally when you do elimination, when we had two equations and two unknowns, we were able to eliminate one of the variables and write the other variable and get a number for it. But in this case, we're still left with two unknown variables. Okay, so how do we deal with this? Step 2 says let's choose a parameter, because we know we're going to get we know the two planes intersect at a line, right? Two planes intersect at a line. So a line is going to have a vector equation or a parametric equation, and that there's going to be a parameter. Okay, so what if, for the sake of argument, let's make x equals t. Let's make that the parameter. Okay, so if that's the parameter, then I'm going to have negative 3. I'm going to make a substitution here, x of t, and then plus 2y equals negative 5. So I'm just basically taking that x, replacing it with a t. Okay, and so what does that allow me to do? Well, if I solve for the other variable, solving for y now, I'm going to just rearrange this and write this as 2y equals minus 5 plus 3t, and then y equals negative 5 over 2 plus 3 over 2t. Okay, so there we go. We have now a parametric equation for y. Okay, so that was step 3, and I don't think I wrote it here. So solve for the other variable, step 3, so we did. Okay, and then step 4, let me just write step 3 again. So y equals negative 5 over 2 plus 3 over 2t. So step 4 says, let's now take this, substitute answers for x and y into the second plane and solve for z. Okay, so what would be my answers? We're going to substitute this y, and we already set x equals t arbitrarily. Okay, so we're going to use that x and y and solve for the third variable z. Okay, so I'm going to go back to the second planes. Here's my equation for the second plane: 3x minus 2y plus z equals 4. Okay, I'm going to substitute. So x is now t, so 3t minus 2 times y. Y is a negative 5 over 2 plus 3 over 2t, and then plus z equals 4. Now I'm going to solve this for z. Let's we can make some cancellations here. This 2 in front multiplied inside cancels with the 2's in the bottom. So I have really a 3t minus make plus 5, and then minus times 3 is minus 3t, and plus, don't forget the z, and that's equal to 4. So then if I rearrange everything here, and if I can see the 3t's cancel, and then I have 5, so z equals 4, take away 5, which is negative 1. Okay. Now, if the t terms didn't cancel, that I could end up having some kind of t value at the end, which is fine too. But here we only have z equals 1, negative 1 rather, and that completes our parametric equation, right? So our parametric form, so the line of intersection, or the two, this is the case where the two planes intersect and it's a line. Okay, so the line of intersection is just the parametric equations we created here: x equals t, y equals negative 5 over 2 plus 3 over 2t, and z equals negative 1. Okay, and before you conclude and say this is the final answer, you should just check, put these parametric equations into the other equation of the plane. So we did 3x. So on this side, we did 3x minus 2y plus z. Use the other equation. So 6 times t, or 6x, minus 4y. So minus 4 times negative 5 over 2 plus 3 over 2t. And then plus 3z. So 3 times negative 1 equals 7. You just want to check the left side equals the right side. And so we have 6t minus 4 cancels with the 2 to get 2, so 2 times 5 is 10, so plus 10, and then we have so 4 cancels with this 2, get another 2 again, so 2 times 3 is 6, so minus 6t minus 3 equals 7, and so 6t cancels with 6t, and 10 minus 3 is 7, so 7 equals 7, the left side equals the right side, so therefore that works. Okay, those parametric equations work. And then if we're asked for the vector equation, then you just convert the parametric into a vector form. So here we have, t, there's a constant of 0, we have the other constant, and we have the other constant. So that's going to be the starting point: 0, negative 5 over 2, and negative 1, plus my parameter t times the direction vector. So here we have coefficient of 1 for t, 3 over 2, and plus 0t, really, in there. Okay, so those are my direction vectors: 1, 3 over 2, and 0. Okay, so there it is. There's my example of finding an equation of a line, the line that's the intersection of two planes. Okay. Okay, let's move on to 3 planes. So in the textbook, you're only going to get a couple of practice problems with 2 planes. The majority of the problems are about 3 planes. So let's talk about consistency. The system of 3 planes is called consistent. So there's a new word: consistent, if it has 1 or more solutions. So you can have 3 planes in one scenario where the intersection of the 3 planes intersects at a point. Okay. So the interesting about this, and again, you have to always, to understand how we're going to be doing the solutions to these, you have to think about their normals. What are the normals to these planes? So I have a normal to this plane here, I have a normal to this plane here, and I have a normal to this plane here. Okay, and then we have okay, and then we have. So what's special about these 3 normals? Okay, so the three normals here, N1, let's call them N1 and N2 and N3. Okay, now if you look at N1, N2, and N3, we have all these vectors pointing in different directions, okay? And they're not parallel, okay? So right off the bat, we can say they're not going to be parallel. They're all pointing in different directions. So one's going up, one's going to the side, one's coming out of the page, that kind of thing. Okay, so we're going to say here that they're not parallel, so therefore they're not equal to each other. They're not scalar multiples of each other. So that's one important property we could say about three planes that intersect at one point. Okay, so then we have another thing that we're going to be looking at, and that is the triple scalar product. Okay, and the triple scalar product here, n1 dot n2 crossed with n3, is not equal to 0. Now, why is that important? Okay, now it'll come to us in the next diagram, but just keep that in mind. Okay, so this triple scalar product is an important thing to kind of review when it comes to the intersection of three planes. Okay, and so here, coming up right now, what if you have three planes that intersect in a line? Okay, so we have a normal, okay, and then we have another normal, and then we have another normal. Okay, now if I look at these normals, like obviously they don't look parallel to me, so they're not, these normals are not going to be scalar multiples of each other. So I'm just using again this k times n2, and I'm just putting L is a scalar value here for n3. Okay, however, now here's the thing. These planes are coplanar, right? If I look at the three normals, the way the planes are oriented, the normals can all act on the same plane, right? You can, so if I if you look at, yeah, like think of this as a, you know, like a rotating wind turbine or something, you know, and as that rotates, you know, imagine those little normal vector arrows, they're all rotating about the same circle, right? About the same plane. And so here's why the triple scalar product is so important, because the triple scalar product for this scenario will equal 0. Okay, now why is that? So, okay, so if you have two normal, let's say two vectors, here are two vectors, and let's say I found the cross product. Let's say this was n2 and n3, and I found the cross product, and the cross product produced this vector. Okay, and this vector, the cross, by the nature of the cross product, that vector is perpendicular to n2, and it's also perpendicular to n3. Okay, now n1, let's say n1 is also on this, is also on the plane here. Here's n1. Okay, now if I were to, now, okay, we don't know n1's on, let's say n1 is, we don't know if n1's on the plane or not, right? The plane made by n2 and n3. Okay, there's a plane being made here. Okay, so I'm going to create another vector, and whoop, okay, here's n1. If n1 is coplanar with this plane, okay, then I would know that's true if I took the dot product with my red vector. And if I took the dot product with that red vector and it's equal to 0, then I know the red vector is perpendicular to n1. And because that red vector is perpendicular to n2 and n3, then n1 has to be on the same plane as n2 and n3. Okay. And so if they're on the same plane, it's like saying, well, all these three normal vectors are, you know, they're all coplanar. And so the situation that happens here is that, that my three planes all intersect at one line. Okay. So it takes a little bit of thinking about that. Okay. there is a situation where all of this may be true, but they still don't intersect at one line. But for the first part of this thing, when we're talking about consistency, again, this is what we're looking for. We're looking for if the normal vectors are parallel or not, and then we're checking to see if they are coplanars. And the coplanar is done by using the triple scalar product. So here the vectors are coplanar, and this one they're not. Okay, these vectors are really facing in multiple different directions, not along the same plane. Okay, then the third case, if we have three consistent planes, if the three planes are coincident, okay, and here we have an infinite number of solutions, right? All three planes are the same. So what we're saying here is plane 1 is a scalar multiple of plane 2, which is a scalar multiple of plane 3. Okay, and all the normal vectors are all going to be pointing the same way. Okay, so n1 is equal to a scalar multiple of n2, which is equal to a scalar multiple of n3. Okay, and any point on one plane, right, on the first plane is also on the second plane and also on the third plane. Okay. All right. Let's look at some examples. Here's a system of equations. Determine the point of intersection. Okay. Point of intersection. What do we do? What do we do? What do we do? What do we do? Okay, so here you have to be mindful of a few things. Okay. Start with what's given. And what's given are these three equations of these planes. And from these equations, I can extract their normal vectors, just like what we've been doing so far. So normal for number 1 is 1, 1, and 2. The normal for number 2 is 4, -3, and 1. And the normal for number 3 is -5, -2, and 3. Okay. All right. And let's look at these normals. It seems pretty obvious to me when I look at, are they scalar multiples of each other? No, it don't look like that. So it's n1 not equal to n2 not equal to a scalar multiple of n3. Okay, so I can't find a scalar multiple, a scale factor that relates one vector to another. I can't multiply by 4 and get the other components, or anything like that. What about the triple scalar product? So here's where you need to determine, are these normal vectors coplanar? Okay, if they are coplanar, then they could intersect at a line. Okay, if they're not coplanar, then they will intersect. They may intersect at a point. Okay, and the question says find the point of intersection. Okay, that clues you in a little bit, but you just want to make sure. You want to check. Okay, because the question could be determine the intersection, and it wasn't specifically saying a line or a point. So we're going to check. We're going to do the cross product of n2 and n3. Okay, and so if we work out the cross product, so here we're going to have -9 plus 2, -5 minus 12, and -8 minus 15, which is equal to -7, -17, and 23. Okay, so there's our cross product. You can use that, the whole trick I was doing, but I'm just kind of shortening the calculation here. So there's my cross product, the triple scalar product now, n1 dotted with n2 cross n3. Okay, equals, so n1 is 1 times -7, and plus n1, the y component is 1 times -17 plus 2 times 23, which is not equal to 0. Okay, so if it's not equal to 0, it's actually equal to 70 or -70. Okay, equal to -70. So it's not 0. That means we don't have coplanar. These normal vectors are not coplanar. Okay, so we're going to have a point of intersection. And so here goes how we solve a point of intersection when we have 3 equations and 3 unknowns. Okay, I'm going to start with these first two, x plus y plus 2z equals 5. 4x minus 3y plus z equals negative 78. Okay. And so it's fine that these equations are not equal to 0. They just move the constant over to the right side. Okay. Now I'm going to eliminate one of the variables here. Let's eliminate x. Okay. If I want to eliminate x here, I'm going to just I'm just going to take equation 1. I'm going to multiply it by 4, 4x, 4y. 2 times 4 is 8. So 8z. And then 4 times 5 is 20. Okay, so it's multiplied equation 1 times 4. So let's call this R1 times 4, and then here's R2. Okay, and then I'm going to say, okay, let's subtract them. Let's subtract both equations. Okay, so 4x times 4x is 0x. Okay, good, x is gone. 4 take away negative 3 is 7y, and 8 take away z, 1z is plus 7z, equals 20 take away negative 78 is negative 98. Okay, solving for what now? Okay, I have 2 variables left over here. Let's just write one in terms of the other. If I divide everything by 7, I'm going to get y plus z equals 14, negative 14. Okay. And then I can isolate one variable on one side. So I could say y equals, did I make an error? Minus 4. No, it's fine. Okay, so y equals negative 14 minus z. Okay. Okay. Hope I did not make an error. No, I don't think so. Okay, let's take a look at another pair of equations. So let's say, so we have to deal with this. We have y minus 4 equals negative 14 minus. I need something to plug that into. Okay, ideally, I'm going to plug that into one of the equations and ultimately to solve for z. But what I need to do first is create a second equation. I have to create a second equation that also contains y and z in it, right? Okay, and the only way I can do that with what I'm given is if I take another pair of equations, I could take this pair, or I could take this pair, the first and third. Okay, so I'm going to take the first and third here. I'm going to do that. I'm going to write here x plus y plus 2z equals 5. And the third equation, minus 5x minus 2y plus 3z equals 27. Okay, now if I take the first equation, multiply that by 5. Let's multiply this one by 5. And if I do that, I'm going to just do it below here. Minus 5. Sorry, that's going to be 5x plus 5y plus 10z. 5 times 5 is 25. Okay, so there we go. I'm going to take these two equations, and what am I going to do with them? I'm going to eliminate the x. And to eliminate the x, I'm going to add them. Let's add both these equations. Minus 5x plus 5x is 0. Negative 2 plus 5 is 3y. 3 plus 10 is 13z. And 27 plus 25 is 52. Okay. So there's my second equation with only y and a z. Now I'm going to take these two answers that I have here. I'm going to substitute one of these equations into the other. Okay, so I already wrote this one here as a y in terms of y. So let's just plug it in here. So 3 times y is substituted with negative 14 minus z plus 13z equals 52. Okay. And then we are going to solve for z. We have an equation with just z in it. So 3 times 14 is negative 42 minus 3z plus 13z equals 52. Minus 3 plus 13 is 10z, and 52 plus 42, if I did this right, 27 plus 2 minus -2 plus 5, 3 plus 13, 27. Were any of these negative? Okay, 52 plus 42. Oh, wait a minute. Oh, I knew there was a mistake. Okay, I caught the mistake. 20 plus 78 is plus 98 plus 14 plus 14. And so this is plus 14. My bad. Okay. Plus, so this makes it plus 42. And then so 52 minus 42, when I bring it over to the other side, is 10. And so divide both sides by 10, I get z equals 1. Okay, I guess just to show you that one silly mistake can throw off everything in this entire calculation. So you got to be very careful here. So there's z equals 1. From that, I can go back to this equation. I can find y equals 14 minus 1, and that's equal to 13. So there's my y as well. Okay, so we're getting close to completing the whole point of intersection. Really, the last thing we need to do is just take one of these equations. We can take the first one here, plug in your y, plug in the z, and solve for x. So we do that here, x plus y, which is 13, plus 2 times z, 2 times 1, which is equal to 5. Solving for x here, x equals 5 minus 2 minus 13, and that's equal to negative 10. So there's my point of intersection. So the intersection. So the intersects. I'm spelling this. Intersection at negative 10, and the y value is 13, and the z value is 1. Okay. Now here's where you do need to check. Okay. There's a checking step. Check this, please. Okay, if you don't check, you might have the wrong answer, right? This point of intersection has to work on the other equations. So if I take equation 2, 4x minus 3y plus z equals negative 78, you check 4 times negative 10 for my x minus 3 times 13 for the y plus 1 for the z equals negative 78. And then the left side, you evaluate the left side, it turns out to be negative 78. So you're good there. And you check the other equation, minus 5x, right? So minus 5 times negative 10, minus 2y, 2 times 13, plus 3 times z, 3 times 1. Is that equal to the right side, 27? And if you evaluate the left side, yes, it does. 27 equals 27. This is a very important step, more so than ever before, because if you forget, so remember I said, look at these. I worked with equation 1. Oops, and undo. I did equation 1, equation 2. Okay, and then if you did that over here, if you worked on equation 1 and then equation 2 again, or something weird, some mistake might happen where you're just looking at just 2 equations instead of all 3. You could end up with the wrong answer. Or if I left the negative 14 here, and I would have a really bad answer for z, but I still would have had a z, and that z would have given me an intersection. But if I didn't check the intersection point with the other 2 equations, and I wouldn't know that I would have gotten it wrong. Okay, so luckily we caught the mistake as we went through, and we got it right. Okay. Example number 3. Determine the line of intersection for each system of equations. So I'm just going to show you an example. What does it mean to find a line of intersection instead of a point? Okay, so here we have 3 more equations. Let's find their normals. 1, 2, and 3 for the first one. N2 is 1, negative 1, and negative 3. And then the third equation, N3 is equal to 1, 5, and 9. Okay, and there we go. Then we have to check, are these normal vectors parallel? Okay, well, the x component, scalar multiple of 1, but that scalar multiple does not apply to the y and z components. So I cannot say that n1 is a scalar multiple of n2 or a scalar multiple of n3? They are not, okay? So not parallel, normal vectors, okay? So what does that mean again? Again, think about the diagrams. We're looking at these diagrams. If they're not parallel, that you could have them intersect at a point, or maybe they intersect at the line. So, but definitely they're not coincident. So that's out of the picture. They're not coincident. So you only have these two scenarios. Now, how do you determine which one of these two scenarios? Well, that's where the triple scalar product comes in. You need to do the triple scalar product. Okay, so let's find n2 crossed with n3. If I find the cross product of n2 cross n3, I will have -9. I'll write it all out. So we have to have -9 plus 15, -3 minus 9, and then 5 plus 1, which is equal to 6, -12, and 6. And so I'm going to take 6, -12, and 6 and dot it with n1. So my triple scalar product, n1 dot n2 cross n3 equals, so n1 is 1, 2, 3, so 1, 2, and 3, each of them multiplied by my 6, -12, and 6, and added together like so. And then when you add them together, I get 6 minus 24 plus 18, which is 0. Okay, now we're getting somewhere. That means that these planes are coplanar when the triple scalar product is 0. Okay, reminding ourselves again, up here, they are if the triple scalar product is 0, then these planes are all these normals are, the normals are all coplanar. They all act on the same plane, and we're looking now at a situation where the three planes intersect at a line. Okay, so let's solve. Let's take a look at what it looks like when you solve it. If I know that they're in a line, I'm going to take my equations. X plus 2y plus 3z equals -4. Okay, and I'm going to take the second equation, x minus y minus 3z equals 8. Okay, and I'm going to eliminate, easiest one to eliminate is x. They all have the coefficient of 1. So let's eliminate x by subtracting both equations. X minus x is 0. 2y take away a y is 3y. So remember, we're subtracting. Whoops. So 2y take away a minus y is 3y. 3z take away a minus 3z is plus 6z. And then -4 take away 8 is -12. Okay. Okay. And here this time, I'm not gonna rearrange this. I'm just gonna keep this 3y plus 6z equals -12. I'm gonna take now, just like before, take the first and third equation, x plus 2y plus 3z equals -4, and take the third equation now, x plus 5y plus 9z equals -16. And yeah, if I eliminate x again by subtracting, x minus x is 0, 2 take away 5 is -3y, 3 take away 9 is -6z, and -4 take away -16 is +12. Okay. Now, the reason why I'm doing this is because this is the same process as if we were doing the point of intersection, but we know we're going to get a line of intersection. And do you notice that these two equations essentially are just kind of like negatives of each other, right? If I try to solve for a y and a z, so if I put one under the other, so -3y minus 6z equals 12, well, if I try to, eliminate one variable to get the other, it won't work because I'm really just going to end up eliminating both variables, right? 0y plus 0z equals 0. 0 equals 0. So this sort of serves as a check that you're not going to encounter a point of intersection. You're just going to encounter a line of intersection. So how do we proceed then, right? we're going to need to, because we're going to produce a line of intersection, I need to produce this parameter t, okay? Just like with the two plane examples. I need to produce a parameter t. So why don't I just say, let pick one of these variables, z or y. I'm going to pick z. Let z equal to t, okay? And if z equals to t, then I can say, okay, 3y plus 6t equals negative 12, okay? And then I can rearrange for y. So 3y equals negative 12 minus 6t, and divide both sides by 3. Y equals negative 4 minus 2t. Okay. Okay. All right. That gives us one parametric equation already. All right. What about another one? All right. I can try to find x perhaps now. Yeah. Okay. I know I already have z equals t as well. So all I need is x. So you just take one of the three equations. These are three that are given to you in the beginning of the problem. Okay, take the first one, x plus 2y plus 3z. So x plus 2y, y is now replaced with negative 4 minus 2t. And then we have plus 3z. So z is replaced with t. And that's equal to the right side, negative 4. Let's solve for x. So x minus 8 minus 4t plus 3t equals negative 4. And then if I rearrange, I get x equals negative 4 plus 8 is positive 4. Negative 4t plus 3t is negative t. Brought to the other side, you get plus t. So there it is, x equals 4 plus t. So here's my parametric equation of the plane. Parametric equation of the line, my line of intersection. So we're going to check. So here's my parametric equation. X equals 4 plus t, and y equals negative, right? Negative 4 minus 2t, and we said z equals t. Okay, now there are always multiple representations of a line, right? So this arises from me arbitrarily choosing z equals t. I could have made y equal to t, and then this entire set may look different, okay? So when you look at the answers at the back of the book for some of your problems, they might say answers may vary because you could get different representations of the same line, okay? The line of intersection I'm talking about here. Now, these parametric equations are good and all, but you do still, again, have to check these parametric equations into the other two equations of the plane, okay? So I'm going to check in the second equation. So x minus y minus 3z equals 8. So if I plug in x, so 4 plus t minus y, which is negative 4 minus 2t, minus 3z, so minus 3t equals 8. And if I resolve the left side, I get 4 plus t plus 4 plus 2t minus 3t equals 8. So yeah, 3t minus 3t cancel, 4 plus 4 is 8. So 8 equals 8. Very good. And then if I check the third equation is x plus 5y plus 9z. So x is 4 plus t plus 5y, so negative 4 times minus 2t plus 9z, so 9t equals negative 16 on the right side. That's my third equation. And let's check 4 plus t minus 20 minus 10t plus 9t, and that looks like the t's cancel. 4 minus 20 is negative 16. So left side, again, left side equals right side. Okay, so that check is important. You want to check that your line of intersection, this is the line of intersection, works, it satisfies all three equations. Okay. All right, so now what happened? What are the cases? Those are the cases that where planes intersect at a point or a line. What about if planes don't intersect? We call them inconsistent if they do not have a solution. Okay, so what if your three planes are all parallel, okay, and two of them are distinct? Then there's no solution, right? So again, these planes all have normals, and they have they can be written as scalar multiples of each other. So that's possible. But if you pick the point P1, it is not on all three planes. Okay, and so there's no solution. There is no solution, no point of intersection. The second picture that you see are three planes. So two planes are parallel. So these two are going to be parallel. They'll never cross. Two sheets of paper, just parallel. And then the third plane cuts right through the two parallel planes. Okay, so here you're going to have one normal vector as a scalar multiple of another, but it's not parallel with the third one. So not equal for one of the pairs, but equal for the other pair. Okay, and now on this one here, three planes, just like the coplanar example, the normals are coplanar, and they're not parallel. And there's a case here where you don't get a single line of intersection, you get multiple lines of intersection for pairs of planes. Okay, this is why it's so important. Like this has the same conditions, right? N1 not equal to Kn2 not equal to Ln3. Okay, and the triple scalar product n dot n2 cross n3 equals to 0. Okay, these are the same exact conditions as the picture that we had up here. Okay, same exact conditions. However, this one only had one line of intersection. But remember, we checked, in my example, we checked that line of intersection with all three planes. That's why it's so important. We checked it with all three planes. Okay. I showed the check with the two planes, but we derived the equation from the first plane, right? It's using the first plane primarily in both of our systems. Here, if you came up with a line of intersection and you checked it with all three planes, it would not work. Okay, and I'll show you an example. Okay, let's just go back for a moment for this example here. So let's look at this one. Here's an example. Describe each system of planes, if possible, solve the system. So if I look at N1, let's extract that one, -1, 1, and 3, and N2 is equal to -1, 1, and 3. Oh, wow, we have the same exact vector for N1 and N2. What about N3? We have, well, 1, -3, and 5, and that does not look like a scalar multiple of the other ones. So these two are parallel, okay, and are they distinct? Yeah, because one is a 2 and the other one's a 4. So parallel, distinct. Okay, so that's what those two equations represent those two planes. The third plane, well, they're not parallel with the other two normals, therefore that plane is going to slice right through my other two planes. Okay, is there a solution? No. Okay, yeah, you see two lines in the diagram, but that's not an intersection for all three planes. Okay, those are intersections for those pairs of plane, but that's not what we're looking for. We're interested in if there is an intersection with all three planes. So not in this case. Okay, looking at the third example. Okay, so here's this last example is an example of this situation. Okay, so if I look at what we're given here, we have x equals 0 as a normal vector, right? So think about, capital A x plus capital by plus capital CZ plus d equal to 0. Here's where only the capital A exists, a times x, 1x. So my normal vector is just going to be 1, and the other two parts are going to be 0 and 0. Okay, same thing, similar idea for n2 rather. So 1y equals 0. So 0, 1, and 0. There is no x and z, no capital A, no capital C. Okay, and then for the third vector, well, we have 1x and 1y, so that's going to be 1, 1, and 0. Okay, now remember, these look like, well, aren't these just linear equations? X equals 0, y equals 0, y plus x. Remember, these represent planes, not lines. Okay, these are equations of planes. You have to keep that in mind too. Okay, so these are not lines, so they're planes. All right, so if I check the triple, so again, first of all, are they parallel? Are they scalar multiples of each other? No. All these zeros here, it's not going to work out. But we do have to check if the triple scalar product is 0, right? So let's find n2 cross n3. Here we have 0 take away 0, 0 take away 0, and 0 take away 1, which is the scalar, the cross product is 0, 0, and -1. And then the dot, the triple scalar product n1 dot n2 cross n3 equals 0 plus 0 plus 0, which is equal to 0. Okay, so there you go. The triple scalar product is 0. It means all of these normal vectors are coplanar. Okay, they all act on the same plane. Okay, think of like, think of the previous page where we had all three planes intersecting at this line. The same idea here. They're all coplanar. Okay, and what happens when we try to solve them, right? Just like, so if we assumed for a minute that I tried to solve this, like there was one single equation of a line that intersect all three planes, well, you could try. Okay, I'm gonna take this. So here, let's write these as equation 1, 2, and 3. And I can try some elimination thing if I wanted to, right? I could write this as x plus 0y plus 0z equals 0, and then the second equation would be so 1x, 0x plus 1y plus 0z equals to 0. And if I eliminated a variable, I couldn't eliminate anything there, could I? Right? So let me take the third equation. I'll write the third equation. 1x plus 1y plus 0z equals 4. And if I eliminated x, okay, so that goes away. 0 take away 1y is just negative y. 0 take away 0 is 0 equals 0 take away 4, which is -4. So y equals 4. Okay, that's already not consistent. I mean, like if you look at plugging that in, that's not gonna really fly, right? And I could do the same thing with the second and third equations. So I could take 0x plus 1y plus 0z equals 0, and then 1x plus 1y plus 0z equals 4. And if I tried to eliminate a variable, I could eliminate y by subtracting both equations. So -x equals -4, and so x equals 4. So there is just no solution here, right? If I plug x equals 4 and y equals 4, it doesn't satisfy all three planes. Okay, there is no line of intersection. So what you really have here is, although the triple scalar product is 0 and the normals are all coplanar, you have this situation, right? So your normals are all coplanar, right? Okay, but you don't have a line of intersection. You have 3 lines of intersection, right, going into the page, right? You're going into the page, all right? And that does not work. It's an inconsistent system. That's not what we're looking for. Okay, so when we solve equations of planes, we're looking for a single point or a single line. Okay, and if you encounter any of these, then yeah, these are inconsistent. Okay, this is by far the biggest lesson of the entire course. It is jam-packed full of different cases of planes intersecting. So maybe you have to go back to a few of the sections of the video, try a few practice problems along the way, and see if you can get them. Ultimately, on the test, when we do the test, it's going to be, I'm going to give you a problem where you do have to find a solution. So you can focus more on the problems that do find a solution, a point or a line of intersection. But it's also good to know conceptually how do you recognize an inconsistent system. All right, that's it. That's the end of the video. And like and subscribe if you like, but really learn. All right, that's it. Ask questions when we reconvene together in class.